Hello students, this is the fourth lecture on cycle group in succession and concluding lecture of a cycle group and about the subgroup to be a cyclic subgroup. Term is if G is a cyclic group of order n and generated by A, then A raised power k generates a cyclic group subgroup of order n by D, where D is the greatest common divisor of n. Statement is if G is a cyclic group of order n generated by A, then A raised power k generates a cyclic group of order n upon D, where D is the greatest common divisor of n. Anyways, let's suppose cyclic subgroup. Of this, we will take the hint here. Let H, H is generated by A power k be a cyclic subgroup of G, which is generated by A of order n. Therefore, we know the theorem because G is a group and A belongs to G is of order n, then order of A raised power any element of the order of any element of G is equal to order of n upon order of the greatest common divisor of n and the order of element. For to find the order of any element that will be obtained, G is a group and is an element of G. Then order of any element of this group will be order of n upon order of the greatest common divisor of n and k is the order of element, right? The index of element, whose order we want. So if you use this term here, you got order of h is equal to which order of you know that order of a cycle group is the order of the element which generates it. So order of h can be written as order of a square k is equal to or k is equal to order of n upon order of this order of n upon order of the greatest number of n I Q is equal to n upon this is the if G is a cycle group generated by of order n generated by A, then A square k generates a cyclic subgroup of order n upon. It's very important here, and you will be using that in solving problems. Next one is let G be a cyclic group of order n. Then for any divisor m of n, again we are discussing subgroup. How can you find this subgroup? How many subgroups a cyclic group will have? Or how many generator will cycle group elements will cycle group will have. So let G be a cycle group of order n. Then for any divisor m of n, there exists a unique subgroup of order subgroup of G of order n. Say then for any positive any divisor m of n, there exists a unique subgroup of G of order n. And this is also called converse of the Lagrange theorem. Show that the converse of the Lagrange theorem holds for finite cycle. So that we are that proof will be let G be a cycle given. Let G be a cycle group of order n generated by A. Therefore, what the meaning of this? This means A generated by G generated by A and the order of this is n. Therefore, order of it is the order of n. G generated by A, order of A is equal to. Now given is m divides n. Divides n implies if m divides n, the remainder will be 0. There exists a quotient q. This integer q belongs to this integer q such that n is equal to mq. Because G is a cyclic group of order n and generated by A, therefore the elements of G will be A1 is A square, so A per K, so A per n is equal to E. Elements of G are of the form of A square K, where K is integers. And also we know that we have produced previous theorem, order of A power k is equal to n upon order of the greatest common order of A power k is equal to order of the group upon order of the greatest common divisor of the order group and index of the element. Not find the order of an element, we can find the this. So this is the general result. Now, if you want to find for any element for this, in case of K, you want to find the order of A is for Q. How can I write this equal to order of the group upon order of the greatest count of n order of group and then that's what this. So this equal to now Q. Q divides n here. Q divides n here. So the greatest count Q and n is equal to Q. Just name it as n upon Q. Which equal n upon Q is equal to n upon Q is equal to how much? This is equal to n divided into n. So order of A is for Q comes out to be n. Therefore, if the order of A is come, therefore there exists an element if a Q of G whose order is n. Supplies what is supply? Supplies. Therefore, if the order of A is for Q is equal to m implies therefore there exists an element Q if a Q belongs to G whose order is equal to m. So we have element belongs to this A to Q belongs to the G and this order comes out here. So it is equal to m. So means this A for Q can generate a subgroup. Therefore, there exists a cyclic subgroup to H. Order of this element is m. Means A to Q to m is equal to E. Means this implies there is a cyclic subgroup H generated by A for Q over there. Means now our aim is to show that this is the only element. So only subgroup generated by A for Q. So let us show that H dash is of order n. That H dash is another subgroup generated by A for L. Be another subgroup of E of order n. Same. Our aim is to show A for Q generates H of order m. Now we suppose that in place of A for Q, we suppose that A for L is another generator which generates the cycle of same order m. So if A is for L generates H dash, then and is of order m, therefore order of A is for L comes out to be m. This implies A is for L. If order of A is for L is m, implies A is for L is for m is equal to E. That is, this implies A is for L. This implies A for L is equal to A for Lm is equal to E. Now applying division rhythm. Now applying division rhythm for dividing L by Q. Then L by Q is equal. This is Q is the Q generates H with this power. So this number cell will be greater than the L, greater than will be Q. So we'll divide here L by Q. So if we divide L by Q, there's a K and R such that L is equal to KQ plus R. Where R is less than 0 less than 12. Now multiply both sides of this question by M. This whole true. And this also 0 less than 2, MR less than and Q is equal to 1. So MR comes out to be less than. From this, E is equal to A square LM. E is equal to take this E square is equal to A square LM. Substitute value of LM here. LM is equal to and separate them. This is the same separate powers. A is for MQ. A is for MQ is for K is equal to A is for MR. A is for MQ is equal to how much? A is for MQ will be equal to into K is equal to A is for N. A is for MQ is equal to how much? A is for MQ is equal to MQ. MQ is equal to MQ. N is equal to A is for N. A is for N. A is for K. A is for K is equal to A is for N is equal to E is for N. But this 0 less than 2 MR is less than N. E comes out to be A is for MR and MR is less than N. The above result is true if MR comes to. Why? Because if A to MR is equal to B, then MR will be the order of A. But order of A is how much? Order of A is n. So it's not possible. So A for MR must be equal to B if MR is equal to 0. And if 0 is equal to B, same as 0 implies R is equal to 0. If R is equal to 0, then L comes out to be L is equal to KQ. So A is for L is written as A for KQ, A for Q, A for Q is for K. So A for Q is for K implies, what does it imply? H dash is the subset of H. Implies H dash is the subset of H means all the elements of this are generated by AQ. All the elements of H dash are generated by AQ, but order of H dash is equal to order of H. Of H dash is equal to order of H. The order of both the sets H and H are the same. Therefore, H dash must be equal to H. The elements of H dash are generated by AQ. Elements of H are also generated by HQ, and they're already the same. Therefore, both the sets must be equal. And there's a group of G. So hence H is a unique subgroup of G of a pair. Next one is prove that every group of prime order is cyclic. Every group prime order is cyclic. Given let G be a group of order P is prime. So we know that the smallest prime number is 2. Since P must be the smallest prime number is 2, only 2 is the even prime number, which is smallest. Therefore, P must be greater than 2. Must be greater than 2. Therefore, G has at least 2 elements. Therefore, if the smallest prime number is 2, so G must have 2 elements. Consider A is not equal to E. We have taken element E is the one element of G, so we have taken the other element. Consider A is not equal to belongs to G, and H is generated by B. Yes, cyclic subgroup G. So cyclic subgroup G. So if it's generated by A, so the order of we know the order of the identity element is 1. So if A is not equal to E, the order of A will be greater than 1. So order of is generated by A, so order of H is equal to order of A. Is cycle subgroup. So order of A subgroup and order of the element which generates it are equal, and that must be greater than 1 because A is not equal to identity element. Order of identity element is 1. Hence, by Lagrange theorem, order of H must divide order of G. Must divide order of G because it is greater than 1. So if order of H divides G, then but order of G is P. So order of H divides P, P is prime number. Prime number, but P prime, therefore order of H must be equal to order of G is equal to P. Why P? Because P is either divided by 1 or by P itself. So P, the order of H is not equal to 1, it's greater than 1. So H must be equal to, order of H must be equal to G. So hence G is a cyclic. G is a cyclic. So every every group that every group of prime order is cyclic. Prime order. The correlation, every group of prime order has no proper sub. Every group of prime order has no proper subgroup. Since every group of prime orders is cyclic, we have proved the previous theorem, and converse of the Lagrange theorem holds for cyclic group. Converse holds for cyclic group, and order of A is equal to P. Every group of prime order of P and P is a prime number. Therefore, P has no proper subgroup. No proper subgroup, and G has no proper subgroup. Every finite group of composite order possesses proper subgroups. Every group of prime order does not have any subgroup, but every finite group of composite order possesses finite subgroups. So let's given it that G is a finite group of composite order. Composite means product of it has two factors. All of this had two factors. Composite, just a composite means four. Composite number is a number which we can compare to prime factors. So this four has two factors. At least. Therefore, if it is a composite order and order is m into n, so order of G given in that is order of G is equal to mn, where m is greater than 1 and due to prime factors different from 1. Our aim is to show that G is a proper subgroup for proper subgroup. For that, the two cases will arise: G is cyclic or G is not cyclic. If G is cyclic group, for that, we have to show that I will show G is a proper subgroup. So, two cases will if G is a cyclic or G is cyclic. Suppose G is cyclic, so it is generated by it has generator and that generated let's generate equal to A, and also if G is finite, therefore order of G must be equal to order of the element is equal to M. So that if the order of A is Mn, then A is for Mn must be equal to E. So this implies A is for Mn is for N is equal to E. So that H is cyclic group generated by cyclic subgroup generated by equal. So the elements of A H is generated by A prime. So elements of A prime A to 2M is what. The order of this H comes out to how much is the order of H? Which is order of H comes out to how many elements this have? N elements. If this A is for M is for N is going to be implies if you take this H any cyclic group which is generated by Abraham, so this will have M N elements. Also, N is a composite number. It's composite number, therefore two. Composite number two is less than equal to N is less than equal to M. Composite number so it could be two or more than two or greater than two brackets. So H is a proper subgroup of H is a proper subgroup of this number. N is a composite number, so N will be kept with two reciprocal. So H comes out to proper subgroup. Now, if G is not a cycle group, if G is not a cycle group, since G is not a cycle group, so G has no element of order M. It has no element. It's not cyclic, so it will not generated by any element. So G has no element of order M. So there is an element A belongs to G such that order of A is equal to K, and K will be it's composite. Therefore, K when K is less than K is less than M. Let H is generated by A cyclic group generated by A. Thus, order of H is equal to order of A is equal to K is less than M. If order of A G is not a cyclic group, then G has no element of order M. If there is element belongs to G of order K and K is less than Mn and greater than 2, and let's go that any group that H is a group generated by A, B of cyclic group generated. So if it generated A and this file, so order of then order of H is order of A is K is less than H, so H is a proper subgroup. Next problem is show that now we will discuss the theory. Show that H consisting of 1 and 0 and n is any integer is a cyclic subgroup of a group G consisting of A, B, 0, C. A, B, C are the numbers such that the number of cases is not equal to the matrix, so second order matrix is not equal to 0 under the multiplication of matrices. Show that this is a cyclic group subgroup of a this group. What shows now HJ subgroup of G under the equation matrix of symbol. Now our aim is to show that H cyclic. If H is cyclic, it must have a generator that A is equal to 1, 1, 0. Now what is our aim? Our aim is to show that every element of H is written in the integer power. Okay, so we multiply A with A. A is equal to A into A equal to A 1, 2, 0, 1. A square into A cube. A square into A, this comes out to be 1, 3, 0. And A square minus 1 is equal to, if I take inverse of A, it comes out to be A 1 minus 1, 0. And so minus 2 is equal to minus 1, 2. So, and if therefore, from this we can conclude, generalize that A1 is equal to 1 and 0, 1 for all integers. Implies this A, H is generated by this element. Imply 1, 1, 0, 1 divided by n, and hence it is a cycle. Determine all the generators of the cyclic group of order 28. Now we will plug in. How many? Determine all the generators of cyclic group of order 28. It's composite number. It is a composite number. It's not a prime number. So it's a composite number, so it can factorize into. So now, G is generated by A of order 28. That G is generated by A 28. So we know the theorem. Order of A is for K is equal to 28 divided by greatest module 28 and K. We know that order of the cyclic group is equal to order of this generator. So order of the generator is A is for K generates this. So and therefore A is for K will generate G. Therefore order of A is for K is 28. Okay. A is generated by this. A is cyclic group. So A is for K also generate this. Not for generator. So generate order of A must be 28. So put the value 28 is equal to 28 over this. So this equation comes out to be very simplified. This comes out to be greatest quantity of 28 and K is equal to 1. So those K's will act as generator which are relative prime to 28. So those power of A will act as a generator of subgroup A which generator of a group which, which are relative prime to 28. So number relative to 28 are the power of A. Power of powers of which powers of A which are relative prime to 28 will act as a generator of G. So therefore 1, therefore 3, 5 and so on, they are the generators. Generator of this group. And order of A for 28 is 28, order of A for 3 28, order of 5 is 28, and so order of 7 is 28, and so order of all each is there. So means we can have a group in which the elements can generate the same. Prove that every group of order 3 is cyclic. Group 3 cyclic. Let G is a group of order 3. 3 order G is 3. Let A belongs to A is not equal to 0 belongs to 0. A is equal to 0. So identity element order of this is equal to 1. A is not equal to 0. Identity element and any element. Let H is a cyclic subgroup generated by A. By A. So order of A is not 0. The order of H comes out to how much? 1, because if is equal to E, order of E equal to. If A is equal to E, order of E is equal to 1. So A is not equal to E, then order of H is generated by A is not equal to E, then order of H must be greater than 1. Therefore, Lagrange theorem order of A H divides order of Lagrange theorem. So order of H is to 3. So order of H is not equal to 1. So order of if H is 3, then 3 is prime number. So divisor is either 1 or 3. So but order of H is not equal to 1. Therefore order of H must come down. Order of H is not equal to 1 because H is not generated by identity element. So Order of H must be equal to 3 because it's not 3. So order of H is equal to G is equal to 3. So H is equal to G. But H G is cycle group. Therefore, G is also cycle group. Every